So in this example problem, we're going to go through how you can use the equations of equilibrium and the the equations of equilibrium to determine our three stresses, sigma x, sigma y, and tau xy. And using those three stresses, we should then be able to calculate our strains. And then from those strains, we can determine whether or not the strain field is compatible. Okay, so we're gonna make some. So we're gonna do this exercise for a cantilever beam that has a distributed load across the top of it. Um, so um, and then we're gonna make a few assumptions. The first assumption is that we're gonna assume that the cantilever beam is in plane stress, meaning there's no stresses along the z-axis. And then we're going to assume that there's no gravity or body forces acting on the cantilever beam. Okay, so first things first. We're gonna do. So the first things first, we're gonna find what sigma x is equal to. So sigma x, or the bending stress in this case, is going to be equal to negative mzy over iz. So I of z is just the moment of inertia, y is just the location relative to the neutral axis. So the only thing that we don't know is what m of z is equal to. So to find m of z, what we can do is we can take a section cut at any location at x. So we can take a section cut like this. So what that would reveal to us is that we have our distributed load W, which is our constant. Right? And then in order to keep this rigid body in equilibrium, we would have to apply a shear force V and a bending moment M. Okay? So if we sum, since we're only really interested in the bending moment, if we sum all the moments about the end of the beam here, and we set them equal to 0, and we say that a positive moment would be counterclockwise, we would get m of z plus the moment due to the distributed load. So the total force acting on the beam would be equal to W times x, and then the location of where the concentrated force would be applied would be at x over 2. Right? So if we rearrange this equation and solve for mz, we get mz is going to be equal to minus wx squared over 2. Okay? So we can plug that in to our sigma x equation here, and we can get sigma x would be equal to negative wx squared over 2 times y over iz. Okay? So if we just simplify that down, we'll end up getting wx squared y over 2iz for sigma x. So the next part of the problem asks us to figure out what is tau xy and sigma y. So we can solve for tau x. To find tau xy, we're going to use the equilibrium equations. So for plane stress equilibrium equation, we have d sigma x dx plus d tau xy dy plus their body forces along the x direction have to be equal to 0. Now we were given that our body forces in this problem can be ignored, so we can set that equal to 0, and then we can say from this equation we can get that d tau xy dy is going to be equal to minus d sigma x dx. So what we end up getting is we'll get tau xy is going to be equal to the integral with respect to dy of minus wxy over iz. Okay. If we perform that integral, what we'll end up getting is we'll get we'll get minus wxy squared over 2iz for tau xy plus, because this is a partial integral, we have to include, instead of adding an integration constant, this will be an integration function, and then that's going to be equal to g is going to be equal to f of x. So we'll get minus wxy squared 2iz plus f of x. All right. So so in order to determine what f of x is, we need to use a known boundary condition. So we know that at y is equal to plus or minus c, so this is the top or the bottom surface of our system. We know that tau at that point is going to be equal to 0, so there's no shear stress at that point. So because of that, we can say that, so we can plug in for tau at plus c, y is equal to c. If we do that here, what we end up getting is we'll get minus wx c squared over 2iz plus f of x. So if we rearrange this, we get f of x is going to be equal to wxc squared over 2iz. Alright, and then we can plug this back in to our equation for tau xy, and we would get tau xy is going to be equal to minus wxy squared over 2iz plus wxc squared over 2iz, and then this can simplify down to wx over 2iz times c squared minus y squared. So the last stress that we don't know is we need to find what sigma y is equal to. So in order to determine what sigma y is equal to, we're going to use the equilibrium equation along the y direction. So we know for plane stress, the equilibrium equation along the y direction is the partial derivative of the shear stress xy with respect to x plus the partial derivative of the y derivative of sigma y with respect to y plus any body forces in the y direction be equal to 0. We know that the body forces in the problem were set to be negligible, so we can ignore them. So we can say that d sigma y with respect to y is going to be equal to the negative partial derivative of tau xy with respect to x. So if we take that derivative of tau xy with respect to x, what we end up getting is we get w over 2iz times c squared minus y squared. We can then integrate the right-hand side with respect to y. So to get sigma y, so we'll end up getting sigma y is equal to minus w over 2iz times c squared y minus y cubed over 3 plus a term which is going to be an unknown function that's only going to be a function of x, g of x. Alright, so we need to use another boundary condition in order to determine what g of x is equal to. So we know that at sigma y at point C, or at the top surface, has to be equal to the force that's applied to the top surface of our beam over the area. So if we go back to the original part of the problem, alright, we have a distributed load, W, that acts on the top surface of our beam here. So we know that the total force on the top of the beam would be equal to the distributed load times the length. Okay? And then the area on the top of the beam would be equal to the length of the beam times the width of the beam, which is B in this case. All right? So using that force and using that area, we can actually calculate what is uh, our normal stress, sigma y, at that point. So we're going to plug those in. So our normal force would be equal to W minus W times L. Right? And then our area would be equal to L times B. So we end up getting minus W over B. At that point is going to be equal to sigma y. Right? And we can set, so the one thing that I'll mention is that because every B, we don't have B anywhere in any of our equations, so we can relate the base B to our to the moment of inertia. So we know that the moment of inertia for a square section is equal to 1/12 the base times the height. So in this case, our base is denoted by the letter B, and the height of our section is equal to 2c cubed. All right. So that's our equation for I of z. We can relate B as being equal to 12 Iz over 8 c cubed. All right. And we can plug that in to our equation. If we do that, what we end up getting is we get that sigma y of c would be equal to minus 8 c cubed w over 12 iz. Alright, and then we can set that equal to our equation of sigma y at y is equal to c. So we plug in the rest of the values, we would get minus w over 2iz times c squared times c minus c cubed over 3 times plus g of x. So we can rearrange this equation and we can solve for g of x. So we get g of x would be equal to minus 2c cubed w over 3iz plus w over 2iz times 2/3 c cubed, which simplifies down to minus c cubed w over 3iz, and then eventually we finally get our answer for sigma y, and we get sigma y is equal to minus w times 2iz times c squared y minus y cubed over 3 minus c cubed y over 3iz. One quick correction on the last equation is that the parentheses should end after the y cubed over 3 term, not after the minus cw over 3iz term. All right. So the final thing here, or the next thing we're going to do is we're going to use the stress-strain relationships to determine epsilon x, epsilon y, and gamma xy. So these stress-strain relationships for plane strain we learned in chapter 1. So all we're going to do is we're just going to plug in our values that we determined in part A of our problem for sigma x and for sigma y and for tau xy. We're just going to plug them in to solve for our three unknowns, or our unknown strains, which are epsilon x, epsilon y, and gamma xy. Okay? So I'm just going to copy down those equations, but all I'm doing is just plugging in those variables, sigma x, sigma y, and tau xy. So after plugging in all those numbers, you should have gotten the following three equations for epsilon x, epsilon y, and gamma xy for part B. So the last part of the problem asks us to determine whether or not the strain field that we determined in part B was compatible. So we're going to use our three strain components epsilon x, epsilon y, and gamma xy to evaluate our compatibility equation. So the first thing we're going to do is we're going to use gamma xy, and we're going to take the derivative of gamma xy with respect to x. So if we do that, what we end up getting is we get 1 plus the Poisson's ratio times e to the iz times w times c squared times y squared. Alright? If we take that equation and we take the derivative of that with respect to y, what we end up getting is we end up getting 1 plus the Poisson's ratio divided by e to the iz times w times c squared ends up becoming 0, and we end up getting minus 2y here. Okay? So that's our first term in our compatibility equation. So the next term we're going to solve for is the the second derivative of epsilon x with respect to y. So we can do that. First, we're going to take the first derivative with respect to y of epsilon x. So we're just going to use this equation here, take the derivative with respect to x. There's only one term that has a x component on it, and it's this first term here. So what we're getting is we get w over 6 e to the iz times with respect to y. I apologize. Looking with respect to y. So we end up getting 3x squared plus the Poisson's ratio times 0 plus 3c squared minus 3y squared. We take the derivative of this equation with respect to y again. What we end up getting is we get w over 6 e to the iz times 0 plus the Poisson's ratio times minus 6y here. So what we end up getting is minus w over e to the iz times y. Right? And then for the last equation we need to solve for epsilon, the second derivative of epsilon y with respect to x squared. So to do that, we're going to take the first derivative of it first. So if we look at that equation, what we end up getting is we get minus w over 6 e to the iz times, we end up getting 0 plus 0 minus 0 plus 6 times the Poisson's ratio of times xy. We take the derivative again with respect to x. What we end up getting is minus w over 6 e to the iz times 6 times the Poisson's ratio times y. So we end up getting minus w Poisson's ratio divided by e to the iz times y. So if we use these three terms that we found for using epsilon x, epsilon y, and gamma xy, and we combine them into a single equation, what we end up getting is minus 2 times 1 plus the Poisson's ratio times w over e to the iz times y. And then if we, on the right hand side, we end up getting minus w times e to the iz times y minus w times e to the iz times y. So what we so there should be a Poisson's ratio on the last term there. So if we divide both sides of the equation by w over e to the iz, what we end up getting is we get minus 2 times 1 plus the Poisson's ratio, which is a constant, times y. Alright, and on the right hand side we get minus 1 plus the 1 plus the Poisson's ratio times y. So the only time that this is true is that this equation will only be true, or compatibility will only exist when y is equal to 0, our strains are compatible. So along the centroid of our original surface, the strains are compatible. If y does not equal 0, our strain field is incompatible. All right. So in short, just to recap what we did, I know this is a long example problem, but it covers all the topics that we did in class, is that we first used our bending stress equation to calculate the stress along sigma x. So once we had sigma x, we could then use equilibrium equation along the x direction to solve for gamma for tau xy. We used our boundary conditions at the top and bottom of the beam for the shear stress to calculate the unknown function of x within tau xy from our partial integral. And then we then were able to solve for tau xy. In a very similar fashion, we summed all the forces along the y direction to find sigma y. Again, we were left with a function of x, and we had to use the boundary condition again to determine the unknown function of x, g of x. Then the next step was really easy. We just used our stress-strain relationships to determine epsilon x, epsilon y, and gamma xy. And then the last thing we did was we just plugged in our strain relationships into our compatibility equation for 2D stress, and we were able to solve for our three cases here. So we were able to determine that the only place that our given strain field or calculated strain field would be compatible would be at the centroid at y equal to 0, and all other places the strain field would be incompatible.